get started with our next topic. So first, I want to just take a moment and look. I noticed 13 of you at least have forked our little example, our package MS example. I'm just going to check in. How many of you have actually tried to do some of those exercises and implement some new methods or anything? Anyone? Anyone? What? Kind of? Well, if you feel confident enough, and I guess you don't have to, but if you feel confident enough, I want you to push whatever changes or tries you attempted to your GitHub version of the package, and maybe we'll look at those after lunch if we have a chance. Okay, so now we are going to talk a little bit about scalability in R. These slides are coming from the folder labeled for Scalability on the Google Drive for Advanced R. So first, how many of you have heard that R is slow or experienced R as being slow? Several, quite a few, okay. And how many of you have attempted or know how to do parallel computations in R? One, two. Suppose that we might want to process a large number of mass spectra. And I use large as a relative term here. My example is going to be relatively small, so I can actually do these examples in a real time while talking to you. So I'm just going to load this MS example package, set a seed so that this is reproducible, and simulate 500 mass spectra. That's a not super large number, but it's enough to just be a little bit interesting. But in reality, we might have a situation where we want to process thousands or even millions of mass spectra, like in the example that Vincent was talking about a couple days ago. So what I'm going to do now is say I want to process these 500 spectra with LFY on my mass spectra list. And familiar with LFY? Refresher, LFY. We just do a sort of list factor. So here I'm going to give it just 1 through 10. If we give it any sort of function, I'm just going to say identity, so it's going to return whatever element it gets. Just apply whatever function we give to every element of that list. So in this case, I'm just giving the identity of this factor 1 through 10. So in each case, it will get give me 1, return 1, give me 2, return 2. It will return those results as a list. So I can apply a more complicated function. This function in this case, since I'm not assigning this function to any sort of variable. And what I'm going to do in here is I'm just going to say my variable is x. It's going to be mass spectrum objects. I'm going to submit that mass spectrum with the baseline of it. I actually add a baseline to these, so I have a reason to do that. Alright, so I'm going to smooth noise. I'm going to remove 5 seconds. That's not too bad. Can we do this kind of computation in parallel? It turns out the easiest problems to parallelize are those that are what we call embarrassingly parallel. An embarrassingly parallel task is anything that just has a bunch of independent tasks, no communication between them. The way that we're going to do that is we're going to use a bioconductor. Firstly, we have a serial backend, so that means there's lots of good reasons that do that, or you do that as a developer. Alright, so let's take a look at our first that actually allows us to do some kind of parallel execution. That's this Snow. Snowparam provides a backend for a simple network of workstations style parallelism. So both Snow, this backend, and then one actually come from some older, this one was originally called Snow, the next came from a package called Multicore, and both of these have later been integrated into a parallel package, a single parallel package actually a package called Parallel that you get automatically that implements these this Snow backend and this multi-core backend, but working with this using the package are not quite as nice and simple as this package. You get a lot more control over the clusters that you can make. You also have to jump through quite a few more to actually run things on them. So this Snow style parallelism works. Snow cluster is just, well, a simple network of workstations. So all that happens is you have a process, which is the one that you're running initially, and this starts some additional worker by running an R script that starts new R processes, and then it creates to those and this is really simple, really generalizable. And so this Snow cluster, this Snow style, can work on any platform, Windows, Mac, Linux, pretty on those just fine as long as you have network connection. Snow clusters, you can also have them set up between multiple machines because it's just communication over a network. So that are the advantages of using this Snow backend. You can have connect between a cluster of multiple machines, and it works on pretty much. The primary drawback to this backend is that you start new fresh R sessions. Each of those R sessions whatever packages you need on those R sessions, and you have to move whatever data you automatically your current R session with those R sessions, you have to actually move that data. Parallel simplifies that dramatically, so you don't have to think about it too much, but it does happen. So whenever you start a job using this Node program, packages you need and move data. So there is an associated. So ideally, you would be using this where whatever you're doing takes long enough that initial startup. Create a new instance of this Node program backend. You can see by default it gives me 2. This is all stuff that I can specify via parameter. Program, since it's an actual character. Theoretically specify. Other things like the number of tabs, and they start using it about one more backend, and so multi-core param works kind of similarly to Snow param, but just differently enough. The multi-core param also works by sessions, but it does it in a different way. The way multi-core param works is it works it's a command essentially that our original R process. The fast way to do that, so there's much backend because the original process is much fresh new R sessions and moving everything back. Drawback just Mac OS use multi-core. It might is that isn't always the case. Our garbage collector will be running the memory changes in one of those R workers that will then have its own memory rather than sharing the memory of the original R process. So theoretically, it's more memory efficient, but in practice, not so much. But we'll talk about how to do that when we talk about working with created just with like so. A lot of the same options as I do with some node param. I can specify the number of workers, the number of tasks, progress bar. There's just a couple other backends that you might run into that I'm not going to talk about in detail right now. So there's a do part, and if you've done any sort of parallel processing in R before, you may have heard of a package called for each. This was a package in R back when they still existed. And for each is a nice package. It essentially is solving a similar problem to what this IoT parallel package is solving. It lets you write a single line of code and then register different backends that code can then use. And so the same advantage, user gets to decide what kind of parallel backend they want, or if they don't want one at all. And so if you're using for each and already have one of these for each parallel backends registered, do par param will use that backend. Another one called batch tools param. This one requires the batch tools package to be installed. If you're working on a high performance cluster where you're using that batch tools package, this batch tools and I'm using a package that has what do I do? So by default, BIOC parallel will already have some backends available. If I want to register a particular backend, do that using. And by default, BIOC parallel will use whatever parallel backend is at the top of this list. And so whenever I register, rearranging the order of this list, what that does is that adds that backend to the list if it doesn't already exist, and puts it to the top of this list. And that means whatever backend I registered most recently is going to be. We can have multiple backends registered, and by default it will use this list. And the way that we access just that first one that's used by default is this BP param function. Something in parallel. Well, I think parallel remains a really easy to do a BP lapply function, and it works exactly like lapply for the most part. It just allows you to run it in parallel. Use lapply, you pretty much already know how to use BP lapply. You can see it looks just like lapply. First argument is a list, or a list-like object. It doesn't actually have to be a list. Is essentially any list-like object that implements methods for length, the single bracket operator and the double bracket operator. So we can use, in our case, we can use our mass spectra list with the, even though it's just not a regular R list, list that is implemented by S4 vectors, and S4 vectors, the package package S4 Vectors has already implemented a length method, a single bracket method, and a double bracket method for simple list. We've inherited all of that because we inherited from simple list when we created this mass spectra list class. So we get all of that for free. So we have a length method. We can subset by single brackets, so we can get the first 5 mass spectra or whatever, and we can subset with the double bracket operator to get one particular mass spectrum, in this case the first one. So X here for BPL apply can be any object that is a function, some sort of function that's the dot dot dot. These are whatever additional parameters you want. And that's different from apply is we see it has this BP argument that specifies use. And the default argument for this is a call to BP parameter. Retrieves whatever the default register is. Is by default, it will grab the whatever backend is at the top of that registered list. But a user can also specify their own BP param if you want to use a different parallel backend for a particular apply. So we have a general backend that's registered used by default. You can also override that default by specifying BP param to try things different. You want to try one backend for one function. Call so the question is if that kind of depends on whether the backends here are actually just specifications for what it actually look like. If we start the cluster, if we start the backend, at that point it is equivalent to the cluster. By creating a multi-core param instance, only when something actually wants to be used that will, on a session get for will those you'll apply one use one of these backends. It will start that cluster. It will start whatever additional R processes it wants to. You do have some amount of control over that. Explicitly try too much, but there is a BP start and a BP stop functions like this that let you know whether that backend is you want to stop it, things like that. This is typically stuff that will take care of on its own. You can start up that cluster, at which point those additional R sessions will be taken, and you'll have those. If you were using the parallel package, do all of that manually and manually start the cluster at some point, apply something to the cluster, manually stop the cluster, and so forth. So just PL apply, which is really just changing two small things, and try to get a here. I'm going to go ahead and run this. All I've done is replace the PL apply, and I've added this argument param. For us, specifying param is this Exactly. At this point, we haven't actually done anything differently, except we're calling a different function that is essentially doing the same function we were using. We can see that we did do something we actually a lot slower. This in my slide, well, right now it took 15 seconds. In my slides, it took 12 seconds. Probably because I added that baseline just now. Or else before we saw with just lapply, it only took 4 seconds. I am using the most recent version of the parallel. I am going to slow down. Kind of overhead associated just with using lapply rather than lapply, because lapply will even serially, it actually slows it down by an unfortunate amount. But the idea is that we actually want that slowdown to be
one of the main reasons examples where we see this time gap, where we are expect to see a time loss. It's also because when we parallelize the jobs, the time required to collect the jobs back and assimilate and give the user the final output, that step is a huge, that step itself becomes bigger than if we do it serially one by one. And this game will not reflect unless we are doing maybe like huge amount.
exactly. So lapply is doing lapply is looks like this. Which has been smooth, reasonable. Sessions. So to be to use a snow backend, whatever problem you're trying to solve should take significantly longer than it takes to start the workers and send your data over to them. So I'll go ahead and do that. Here, specify that I want 4 workers. There is a function in the parallel package called detect cores. So if you want a way to program require a way to call just a slightly more programmatic version of the package. Ram equal to minus. You can see here, this is just long enough to see some advantage running this. see that doing for example, either failure URL, a multi-core param created by a fork. And here I'm example in this case, that I have looked good practice to do it anyway. ETL apply in case someone, whether it's you or your user, changes whatever packet you're using to we can't because someone says we can't work. Yes. And we got faster at 0.8 seconds. So faster than snow param. Multi-core param, you have to start fetching our packages and send data. This fork process is just faster than that. So, we're still a little bit slower than the base LFI version, but if we were running this on, say, millions of spectra, I can assure you this would actually be faster. Yes, so the question is, how is BPL apply splitting our original list to send it to the workers? For instance, so we have the number of workers, and then we also have the number of tasks. The number of workers is the number of nodes additional ARC sessions to create. The number of tasks is essentially how many different jobs will be sent to those clusters, which basically corresponds to how many different chunks our vectors or our list will get split up into. You can see the default here is 0, which just means BPL apply IOC parallel will determine this automatically, just depending on the number of workers you have. You can specify the number of tasks that you want. So here I'll create a multi-core param with workers, 4 workers, and tasks. So that should mean my initial list gets filled with essentially 10 chunks that then gets better or worse. Looks like it was about the same. In this case, it didn't make a difference. It can make a difference. It is very large. One argument is that actually first I will use the default. It's 0% right now. So that progress bar is equates according to the number of tasks rather than the number of elements in your list or the number of workers, or anything like that. So depending on line, if it's important to you to have so the progress bar is updated. So here, this progress bar should update in increments of 10. More workers, some of those kind of just at the same time. That is something to doing what?
Like a queue type.
Let's see. So a lot of the more advanced options I know you can control from the parallel package. I'm not sure how much of that is available in BioC parallel, but let me show you, for example. So we're working with we're creating a cluster from scratch using the base R parallel package. You get a bunch of different options for how you want to apply things on your different nodes. So for example, cluster apply here. Virtually it's completely unrelated to the apply function. It has nothing to do with applying things over the rows or columns of a matrix. That's parse R apply or parse C apply down here. Cluster apply, you just give it a function and it runs that function on each individual node. And you can see a few of these are appended with the LB. Those are load balancing ones that will try to do load balancing. I'm not sure what the default is for the other one. So it gives you a little bit more control over that. There is, besides BPL apply, other options in BioC parallel itself for how to do the iteration. So BPL apply is just one option. Apply from base R, there's a BP apply, which will iterate over multiple the elements of multiple lists at once. Basically, a multivariate version of lapply. So that's one that BP iterate. So with BP iterate, rather than iterating over elements of a known list that we already have, with BP iterate, what you actually pass it is some sort of iterator function. And what BP iterate will do is it will call this iter, or iterating function, and that function is supposed to return some chunk of the data that then gets processed, that then gets worked on. And so that's something that's especially useful if you're, say, not exactly sure how much data that you have, or you're working with some kind of streaming data. You have to be able to write some sort of function that will go and retrieve some chunk of data that can be worked on. But here you don't have to have the entire list or specify a list that will then get chunked. Here you just have to specify some sort of function that will retrieve a chunk of data, and then it will do some sort of processing on that. Does that help answer most of the question, more or less? Anything else so far? Okay, so a few general notes on using lapply, or BioC parallel, excuse me. Most of what we covered just now was really quite simple. Essentially, all you have to do is use this BP lapply function in place of lapply, and then allow users to register whatever backend they want. There are a couple of good practices to follow if you do this. So it's recommended that you always expose this BP param argument. So you don't want to call BPLApply inside one of your own functions and specify the backend yourself. Because for one, the user may not have that backend, they may not want to use that backend. You always want to give the user the option to control what kind of parallel backend is being used, both through an argument in the function, and also through the system of these registered backends. So if you write any function that at some point calls BPLApply or BPMApply or BPiterate or one of these functions, you should have a BPparam argument. The default should typically be BPparam. I suppose that part is negotiable, but you should at least have that BPparam exposed so that the user can specify it. Again, no assumptions should be made about what backend that your users will be using. So for example, with SnowParam, I required MS example. I think this code might still work if I don't do that, but it's always safe to do that because I can't necessarily count on all of the packages being loaded onto worker R processes. I can't assume that any particular data will be available. There are a few ways that there's a few things that determine what data is made automatically available on the workers. So you need to make sure all the packages and data that you need are available on the workers. And the way that BPLApply and these other BIOC parallel functions do this is firstly the arguments of the function, whatever function you give, any arguments to that will be made available on the workers. So quite obvious on the spectrum, argument S that corresponds to whatever mass spectrum I'm working on. Of course, it's safe to assume that I'm going to have access to that mass spectrum. But if there are additional arguments to that function and you specify those in the call to BPLApply or BPMApply, any of those arguments will also be serialized to the workers if necessary, and you can count on those being available. The environment of the function, so we talked about how functions have an environment associated with them. The environment of the function, if it is not the global environment, will also be serialized to all of the workers, and you can count on the environment function being available as long as it's not the global environment. Lots of things end up in the global environment, so by default the global environment is not automatically available. With multi-core it happens to be just because of the way multi-core works, but the function, if it's the global environment is not available, but if it's if you're using apply inside your package, well, all of your functions in your package share that package's environment. Your package has its own environment, and so all of your functions and methods in your package will have that environment associated with them. And so, say, if I had this code as part of my MS, I actually need to do this here because the environment or whatever function I'm using is already in my package. So you can count on the environment of your package being available as well. So if you do require any other packages that aren't your own package, you should make sure those are loaded as well. And the main, probably the easiest way to make sure you have access to whatever variables or data that you need is to just construct whatever function you get to BPLApply such that anything that you need as an argument. Etc. Suppose I create some variable called meta, or let's say exponent. This is the name of my experiment. So say I wanted to do So I'm trying to do this. Which means that BPL applies a new pressure is getting whatever arguments to this function will be made available. So S, my mass spectrum, that's available. But when I go to X name, well, that's a variable I made in my current art session right now. It's in my global environment. The environment of this function that I'm using here is also the global environment, but because the global environment isn't serialized to the workers, I don't have access to X name here. So I can't use this variable on the workers because they don't have it. So the simplest way to deal with this, you could manually it's just takes anything that you need as one of its arguments. Here, as one of my function's arguments, an argument to BPL apply as well, so it'll get passed to this function. It's an argument of the function that I'm giving to BPL. It will get serialized and it will be available. So we'll have this particular metadata. You can see it available. You can see it. And then the last thing is, well, we kind of saw a little bit of this, but parallelization isn't worth it. You have smaller functions. Otherwise, you're not really going to see the advantages that at least this style of parallelism gives you. Right. Some parallelization. Generally want to parallelize the big functions that will be time for each individual takes a long time compared to the initial overhead of starting out. The end of this little segment on biocene parallelism. Any questions on any of this?
So for the multi-core function, in our example, you did workers equals to 4. So I believe that the more the number of workers, the job will be distributed among that many workers.
The limit on the number of, well, firstly the question was, is there a limit on the number of workers and what is the relationship between the number of workers and how fast all of this is? So firstly, there's the limit on the number of workers, I believe, would just be the number of socket connections that R can create. I'm not exactly sure what that is. If I has anything to say about that. I'm not sure. You probably want the number of nodes you have. As far as I know, there's not a particular upper limit that you would reasonably run into until you're working on a very large high-performance cluster. In most small situations of that, I don't think there would be a particular limit that you would have. Here I chose 4 because I have access to 4 cores. And so that's the most so if I have 4 cores, I can have 4 processes that are running more or less simultaneously and can gain the max amount of efficiency from each of those different cores. So the number of workers here should typically just be the number of cores or the number of nodes you have across your one machine or however many machines. All of this is running locally on my machine. Workers does not correspond to the number of machines. The number of workers is just the number of additional R sessions, the number of nodes. So here, this is all being done locally. Also, use this kind of thing with for loops, and it depends on how you're using the for loop. P4, for instance, you just directly translate from a for loop into this. You would have to set slides where I do something that is kind of for loop like. Essentially, you would apply over, say, some number of indices and then do something inside that. But it depends on what you're using the for loop to do. So if your for loop is constructed such that each iteration depends on what you did in the previous because that's not inversely parallel, those are not independent tasks, that won't work. If your for loop is set up such that each iteration is pretty much independent of the others, then you could easily translate it to something like this. So it's fairly straightforward to do something like that. Alright, yeah, so this isn't something that I had really done myself much, but this, if you look at the vignette from the BioC parallel package, it describes setting up a snow param instance with, in this case, multiple machines. Let's see. Yeah, so the way that you can specify that is here it's giving a vector of the hosts, just giving the host names of the machines. And if you have the same machine appearing multiple times in this list of hosts, that just means that machine will have that many number of workers on it. Another question?
Yeah, I was wondering if there is a trade-off as you approach the number of cores, the number of workers, because you need to allow some processing to function as a traffic cop.
Right, so the question is again on the trade-off between the number of workers and the number of cores or the number of machines. And so yes, there is ideally with parallel processing, we would see essentially a linear relationship with workers and the number of cores we have and the speed up that we would expect. Realistically, it doesn't actually look like that. It's something that falls off, and we add more workers to it because they can't propagate. As well as the need to move things back and forth, move data, collect results from those numbers. It's a little bit of a trade-off, and some of that will depend on how big your data is, how running on the same machine, so there's lots of variables that go into that. So if you're running this on, say, a cluster that lots of other people are using at the same time, there will it's kind of too definitively what that relationship looks like, and there will be some kind of trade-off. And in the simplest case, it's usually safe to just set the number of workers really the best starting. Okay, so I have I'm going to look at Amazon. Okay, so if you're on GitHub, for example, I have a branch called BioC Parallel. Kind of one change to sim spectra function spectra for 5,000 spectra. You can now do that in parallel. A bit faster, potentially doing it serially. See that we did. It's changed. You can look at this commit on GitHub and see all that I changed is I've changed what I had here as a replicate before. I'll apply when I'm just iterating those numbers. That sequence doesn't end up mattering because I'm using BP, I'll apply, which means supposing the BP param function to return the backend. Well, firstly, I updated the document to include the new BP argument. I import the parallel because that ended up namespace generated from my route. I added BioC parallel to my list of depends in my description as well. So that's just an example of a really simple case of adding some parallel support. This little example package. Note here, I have this little comment here. One problem with the function as I have it now is simulating spectra. Obviously, simulation is going to use some sort of random number generation. Parallel random number generation is one of the trickier things. So in this case, for this example, I didn't do anything to actually account for that because I keep this example relatively simple. But so here just, and there's more details on this elsewhere, but just a reference from the documentation of the parallel package. If you want to work with multiple random number generator streams, that can be used in parallel. There is an RNG, there's a random number generator you can see here called Lecurier CMRG. Different options for what kind of random number generator you're using this RNG kind function. If I scroll down here, it gives me this documentation for RNG kind, gives me a list of the different possible options that I is here this Lecuyer CMRG particular because it provides support for multiple RNG at once that we can on GitHub if you're inclined. What you need to do is you need to make sure that your user has set the random number generator to this Lecuyer CMRG random number generator. That's the only way that their results will be reproducible if they set the seed. And then you want to generate as many RNG streams as you're going to have jobs to do, essentially. So for simulate spectrum, this is maybe not the most straightforward way to do it, but we actually have to pre-generate a random number generator stream for every single mass spectrum that we want to simulate. So here, I simulated 500 mass spectra. That means if I was doing this in parallel, my SimSpectra functions should create 500 random number generator streams that then get passed. There is the next RNG stream that will just generate additional random number generator streams from this particular random number generator. It has some additional options for setting this on clusters and stuff. And so you can see, at least I added a little bit of code around this in my package where I see however many random number generator streams I want or I need to get. I iterate through all of the ones that I need, getting a new RNG stream, and then at some point I need to pass those seeds into the function that is going to be called on the workers as one of the arguments, and on the workers they will need to assign whatever that seed is to the .random.seed variable in the global environment. If a user or anyone sets a seed, there is a hidden variable called .random.seed in the global environment, and that is what you would need to update on the workers. And so if you do all of this correctly, when someone calls .setSeed on your main process, and then you do something in parallel, as long as they have the random number generator set to this particular kind, then their results should be reproducible, even in parallel. It's quite a few additional hoops to jump through, but it's something that you need to do, unfortunately, if you want to have reproducible random numbers in parallel. And again, that's about the level of detail I have time to go into on that. There's more documentation on the bioconductor mailing list and a little bit in the parallel package itself to tell you a little bit more about that. Any general questions on that? So that was our talk on parallelism and how to do parallel computing in R. Now the next kind of question to think about is, well, okay, we have thousands or millions of mass spectra. We can do something to them in parallel, but what if we can't actually load that data into memory, or just generally, how do we deal with larger data like that in R? And you saw Barrett yesterday talked a little bit about that. So you saw one possible approach using Sparkly R, which is moving stuff to the cloud. I'm going to be talking about probably slightly smaller data than he works with. I'm going to talk about stuff that you can do locally. So if you have access to a cloud and you can use Sparkly R or other tools like that, that's great. Move stuff to the cloud. I'm going to talk about stuff that you can do locally on your own machine to try to deal with large data on a single machine. So I'm going to start with essentially the same example from before. I'll go ahead and add this baseline again. So I want to do some sort of processing on this list. We just learned that we can use FiOC parallel BPL apply to do this in parallel. This is how we could do that. But what if our spectra list is very large and either we can't load this into memory, or once we actually try to do this in parallel, then we start immediately running out of memory. So some thoughts on our quote-unquote big data and parallel computation. You can see I put big in quotes here because everyone's idea of big data is a little bit different. Again, I'm not going to be talking about cloud computing right now. I'm talking about some file-based methods that you can do on a local machine. So some difficulties when working with bigger data sets in R. Most R functions expect your data to be available in memory, and R provides, there should be a no here, if you couldn't notice, or it should be R provides no core functionality for working with large data. That's kind of a mistake that changes the whole message of that bullet point. But R provides no core functionality for working with large data, so you're kind of on your own, or at least in the hands of package developers. And then beyond that, parallel computation compounds this memory issue. So worker R sessions cannot share the exact same R objects that you have in your main session. So pretty much always some sort of duplication happens when you go parallel in R. Snow backends, you will end up sending copies of at least segments of that data to the workers. I think BPL apply will try to do it at least a little bit intelligently so that the workers just get the chunks that they need. In theory, forked multi-core backends should be memory efficient because ideally they can share the same memory as your original R process. In practice, this frequently doesn't work out this way because once the memory in one of those R sessions diverges, then it will have its own memory space separate than your original one. And with R as garbage collector and creating new objects and things like that, that happens a lot more often than it should. So ideally, multi-core should be memory efficient. In practice, I've always found it to be a huge memory hog, and you end up with multiple copies of your data set everywhere, which is not a good thing when your data set was already very big. So ideally, we'd like to use some kind of memory efficient data structures that we can easily share between our sessions without having to move that entire data set into memory and then to those additional R sessions. Based backends that you can use from some packages on Bioconductor. So there's two packages I'm going to be talking about. One of them is, well, first one is kind of two packages that go together, HDF5 array and delayed array. It's by some of the core infrastructure, and then HDF5 based matrices. This idea of delayed. So there's this delayed array package, and some of this package doesn't provide for working with file-based matrices. What it provides is essentially a wrapper matrix-like object. This matrix-like and immediately do something like subsetting, actually very large matrix. Subsetting doesn't actually creates essentially instructions that say, hey, when I actually ask for this data, this particular subset of the data, or if I say want to add something to all of the columns or something like that, that operation also doesn't actually happen until I request the data. A delayed array terminology, they say when the data is requested. If 5 array. by providing an HDF5 backend for delayed view an HDF5 array matrix and a few other similar objects. How many of you have at least heard of the HDF5 format? HDF5 is just a scientific format that is designed to be relatively flexible and lots of different kinds of data types. The main advantage of it is just that it's already a fairly widely used format in the sciences and engineering and things like that. More recent versions of MATLAB, for example, if you save an object in MATLAB, that is usually stored in some sort of HDF5 object. So there's lots of support for working with these HDF5 files. And they are designed to be relatively efficient in terms of extracting data from that file and loading it into memory whenever you want. So they're designed to be relatively efficient at that, and there's lots of ways that you can control that, such as setting a chunk size for how the data is read, things like that. More complicated situations than I'll have a chance to go into right now. Essentially, the idea is they're building on this existing scientific file format and using it as a backend for a file-based matrix or array. So that's one package that you can use, this HDF5 package. There's another package, it's actually a package I wrote called Matter. And the idea behind Matter is to provide a very flexible framework for working with binary files in essentially any kind of possible binary format that you might end up with. So the idea behind Matter is that if you know the structure of a binary file, you can work with it as a matrix or an array or a list or represented in R essentially however you want. And this is something that I ended up developing out of a need or desire to support the IMZML format for mass spec imaging. With mass spec imaging, we have this extension to the MZML format that many of you probably are already familiar with, called IMZML. IMZML breaks the data into two different files. One just has all of the experimental metadata, as well as information on where in a binary file, which is a companion file, we can actually find the intensities and the MZ values for the mass spectra. So we have a metadata file and then a binary file. The metadata file tells us where inside that binary file we can find the actual mass spectra information. So if I want, say, the 100th mass spectrum in this experiment, I can read the metadata, find out where in the binary file that mass spectrum is located, and read just that specific mass spectrum. So that's the idea behind IMZML, and I wanted to come up with some sort of way of working with that data really easily in R, so that I can just represent an IMZML file as a regular matrix and say whatever column I'm working with, say the 100th column, that corresponds to the 100th mass spectrum in this file, and I can just access it like a matrix. No, I do not. I don't require the binary be in a separate file. As far as I know, in MZML, you can actually embed the binary part inside a binary tag inside MZML, and I don't want to deal with that. Theoretically, if you have all of the information available, it should be trivial to create a matter object that works with an MZML file, as long as you're able to parse the metadata and know where the spectra are stored. That's all the information that you need to create your own matter object that points to the data and works. So there's no reason you couldn't do it on your own. It should be relatively simple. So that's the idea behind the Matter package. It shares a few ideas as a delayed array and HDF5 array package. Say basic are delayed in the same way, so that if I want to add 1 to every element in a, say, 10 gigabyte matrix, well, we're not actually going to do that right away, but once we actually ask for certain elements of that matrix, then we'll add 1 to each of those. So certain operations are delayed and don't actually happen until we actually access the data. So before I go ahead and go into examples on this, we're pretty close to lunch, I think. So on that note, that summary, I'm going to stop here and we'll come back and work on the examples after lunch.